Welcome, weary traveler, to a quiet corner of the cosmos, a place where the universe whispers its secrets and the gentle hum of discovery lulls you into a peaceful slumber. Here, with the sleepy scientist, we don't rush through the wonders of the world. Instead, we invite them in, softly, allowing their grandeur to unfurl like a calming dream. Tonight, as you settle in, perhaps nestling deeper into your pillow, or letting your eyes gently drift closed, we're going to embark on a journey that begins with a question as vast as the oceans themselves. A question that, once understood, will deepen your connection to the rhythmic pulse of our watery planet. Why is the ocean salty? It's a question that brings forth images of crashing waves and the crisp taste of sea spray, a testament to a profound, yet often unexamined, natural process. As you relax, let your thoughts drift, much like the gentle currents that stir the deep. Imagine yourself standing on a vast shoreline, the endless blue stretching before you, the rhythmic sound of waves a constant lullaby. You might dip your fingers into the cool water, and instantly, a familiar taste greets you, the unmistakable tang of salt. It's a taste that defines the ocean, a taste that sets it apart from the fresh water of rivers and lakes. But where does this salt come from? How does it accumulate in such immense quantities, despite the continuous flow of fresh rainwater and rivers pouring into it? We won't rush to the answers. Instead, we'll explore them with the same slow, deliberate pace that the tides maintain in their ancient dance. This isn't about memorizing facts, it's about understanding, about feeling the profound elegance of the Earth's natural cycles, and letting that understanding guide you towards a truly restful state. So, breathe deeply. Let your muscles soften, and prepare to unravel one of the most fundamental mysteries of our planet. Not with effort, but with quiet curiosity. Our story, like many great Earth tales, begins with something incredibly simple, yet profoundly powerful: water. Think of a single raindrop falling gently from a cloud. This raindrop, at its very essence, is pure fresh water. It has evaporated from the ocean, leaving all its salts behind, rising into the atmosphere, condensing, and now returning to the land. As this droplet, and countless others like it, descends and lands upon the vast continents, its journey begins. This is the very start of the water cycle, a continuous, silent journey that shapes our planet and, in its profound simplicity, holds the first secret to the ocean's saltiness. Imagine this pure rainwater landing on a mountain, perhaps a gentle hillside, or even a rocky outcrop. As it touches the earth, it doesn't just sit there. It begins to move, sometimes as a thin sheet flowing over surfaces, sometimes seeping slowly into the ground, and often gathering into tiny rivulets, then streams, and eventually, mighty rivers. As this water makes its journey across and through the land, it acts as a gentle yet persistent solvent. It interacts with the rocks and soil it encounters along its path. Think of rocks as complex compositions of various minerals. Many of these minerals contain what we commonly call salts. Not just the table salt you might be familiar with, sodium chloride, but a wide array of other chemical compounds that dissolve when exposed to water. As the rainwater trickles over and seeps into the ground, it comes into contact with these minerals. Over time, and with countless interactions, the slightly acidic rainwater, it naturally picks up a small amount of carbon dioxide from the atmosphere. Forming a weak carbonic acid begins to dissolve tiny, almost imperceptible amounts of these minerals from the rocks and soil. This process is known as chemical weathering. It's a slow, relentless sculptor, tirelessly breaking down the Earth's crust. As the water dissolves these minerals, it picks up their constituent parts, transforming solid rock into invisible, dissolved ions. These ions are charged atoms or molecules, now suspended within the fresh water. The most common ions picked up in this manner include sodium, chloride, magnesium, potassium, calcium, and sulfur. Each type of rock, each type of soil, contributes its own unique blend of these dissolved passengers to the traveling water. Now, follow these water droplets, laden with their newly acquired dissolved cargo. They flow from tiny trickles into small streams, which then merge into larger creeks, and eventually coalesce into grand rivers. These rivers, like vast, slow-moving conveyor belts, tirelessly carry their load of dissolved salts across the continents, flowing ever downwards, always seeking the lowest point. And where do these mighty rivers ultimately end their journey? They flow, inevitably, into the ocean. So, imagine countless rivers around the world, from the majestic Amazon to the mighty Mississippi, from the winding Nile to the sprawling Yangtze, all constantly pouring their freshwater contents, along with their invisible cargo of dissolved salts, into the vast global ocean. This process has been occurring for billions of years, ever since rain first fell upon a cooling earth and rivers began to carve their paths across the land. Each drop of river water might seem to contain only a minuscule amount of dissolved salt, barely noticeable to our taste. But the sheer volume of water flowing into the oceans, day after day, year after year, century after century, means that an enormous quantity of these dissolved minerals is continuously being delivered to the sea. Consider, as you relax deeper, the silent work of this fundamental process. The rain falls, pure and sweet. It touches the land, and in doing so, begins a gentle chemical conversation with the rocks and soil. It picks up their hidden essences, their dissolved secrets, and carries them on a long, slow journey towards the sea. The rivers become conduits of these dissolved minerals, tirelessly ferrying them from the highest mountains to the deepest ocean basins. This continuous input of salts from the land, carried by the never-ending flow of rivers, is the very first and arguably most significant contributor to why the ocean is salty. It's a natural, ongoing process, a quiet testament to the Earth's dynamic cycles. Let the image of countless streams and rivers winding their way across the continents, each one carrying its invisible cargo of dissolved minerals towards the vast, waiting ocean, settle peacefully in your mind. This is the origin story of ocean salt, a journey that begins with a single raindrop and culminates in the boundless, briny deep. Feel the quiet power of this endless cycle, knowing that the very essence of the land is continuously being transported to the sea, shaping its unique character. Rest deeply now, with the gentle flow of Earth's rivers, carrying their ancient secrets to the ocean, guiding you towards a truly peaceful slumber. Welcome back, peaceful traveler, as we continue our gentle exploration of why our vast ocean is salty. In our last quiet chapter, we trace the journey of pure rainwater, beginning its incredible work of dissolving minerals from the land, carrying these invisible salts through rivers, and eventually delivering them to the boundless sea. Now, as you drift even deeper into your serene state, let us turn our attention to a powerful, yet often hidden source of ocean salinity. A source that breathes from the very depths of our planet, undersea volcanic activity and hydrothermal vents. As you settle into your comfortable spot, feeling the quiet stillness of your surroundings, imagine the deep, dark floor of our mighty oceans. Far beneath the sunlit surface, where the weight of countless miles of water presses down, lies a dynamic and fiery landscape. Here, the Earth's tectonic plates, those colossal segments of our planet's crust, are constantly moving, pulling apart in some places and colliding in others. It is along these spreading zones where new oceanic crust is being formed that we find a remarkable and vital contributor to the ocean's chemical makeup, the constant interaction between seawater and the molten rock beneath the Earth's surface. Picture a fissure, a crack, in the deep ocean floor. Through these cracks, cold seawater slowly seeps down into the Earth's crust. As this water descends, it gets closer and closer to pockets of searingly hot magma, the molten rock from the Earth's mantle. The water heats up to incredible temperatures, sometimes reaching hundreds of degrees Celsius, far hotter than boiling water on the surface. But because of the immense pressure at these depths, the water remains in a liquid state, not boiling into steam. This superheated water becomes incredibly reactive. As it heats up, it begins to dissolve a whole new suite of minerals from the surrounding oceanic crustal rock. Unlike the relatively gentle chemical weathering on land, this process under the sea is much more intense. The hot, acidic water acts like a powerful solvent, stripping elements from the rock. Simultaneously, other elements already present in the seawater are removed as they react with the hot rock and precipitate out of the solution. It's a dynamic chemical exchange, a silent conversation between the water and the very bones of our planet. As this superheated, chemically altered water continues its journey, it eventually finds its way back up to the ocean floor, often erupting through towering chimney-like structures known as hydrothermal vents. These vents, sometimes called black smokers or white smokers depending on the minerals they release, gush plumes of mineral-rich, superheated fluid directly into the deep ocean. Imagine dark, shimmering columns rising from the abyss, carrying with them a complex cocktail of dissolved substances. What kind of salts do these undersea volcanoes and hydrothermal vents contribute to the ocean? They bring a different, yet equally important, array of ions. While rivers primarily deliver ions like sodium, chloride, calcium, and bicarbonate from weathered continental rocks. Hydrothermal vents are significant sources of elements such as sulfur, often as sulfides, iron, manganese, copper, and other trace metals. They also introduce dissolved gases. Conversely, some elements, like magnesium and sulfate, which are abundant in normal seawater, are actually removed from the water as it reacts with the hot rock beneath the vents. So these vents are not just adding to the ocean's saltiness, they are actively involved in a grand chemical exchange, cycling elements between the Earth's crust and the ocean. This continuous process of seawater circulating through the oceanic crust and emerging through hydrothermal vents is a constant and significant input of dissolved minerals into the deep ocean. While it might not contribute as much sodium chloride, the common table salt, as rivers do from land-based weathering, it is absolutely vital for maintaining the overall chemical balance and diversity of ions in the ocean. It's a powerful hidden factory, endlessly processing the Earth's interior and releasing its mineral secrets into the vast liquid realm. Consider the sheer scale of this activity. There are vast systems of mid-ocean ridges crisscrossing the entire globe, thousands of miles long, where these processes are constantly at work. From the mid-Atlantic ridge to the East Pacific rise, these undersea mountain ranges are dotted with countless hydrothermal vents, each one a tiny geyser of chemically altered water, continuously enriching the ocean with its unique blend of dissolved elements. It's a testament to the dynamic and interconnected nature of our planet, where processes far beneath our sight profoundly influence the characteristics of the world above. Imagine, as you drift deeper into your restful state, the silent, scorching hot world of the deep sea. Picture these towering chimneys, glowing faintly in the pitch blackness, spewing their mineral-rich plumes into the surrounding cold water. This unseen geological activity, far removed from the sunlit surface, is a fundamental part of why the ocean is salty, contributing a vital array of elements that complement those delivered by rivers. It's a powerful, subterranean breath of our planet, constantly replenishing and rebalancing the chemical composition of the greatest body of water on Earth. This continuous input from undersea volcanic activity highlights that the ocean's saltiness is not a simple phenomenon, but a complex tapestry woven from multiple sources. It's not just the result of land erosion, it's also deeply connected to the fiery heart of our planet, a reminder that the Earth is a living, breathing system, constantly interacting with itself on grand, interconnected scales. This ongoing process has been shaping the ocean's chemistry for billions of years, contributing to its unique character and, in doing so, creating the very conditions that allowed life to flourish in its depths and eventually emerge onto land. Let the image of these hidden, fiery vents, deep beneath the calming waves, settle peacefully in your mind. This is the profound secret of the ocean's subterranean chemistry, a continuous flow of minerals from the Earth's fiery core into its watery embrace. Feel the quiet power of this endless cycle, knowing that the very essence of the deep Earth is continuously being transported to the sea, shaping its unique character. Rest deeply now, with the gentle murmur of the deep ocean, where unseen volcanoes contribute to the ocean's ancient saltiness, guiding you towards a truly peaceful slumber. Welcome back, peaceful traveler. As we continue our gentle exploration into why our vast ocean is salty, we've journeyed through the unseen paths of rainwater dissolving minerals from the land and delved into the fiery depths where undersea volcanic activity adds its unique chemical breath. Now, as you drift even deeper into your serene state, let us turn our attention skyward to the invisible embrace of the atmosphere and discover how the very air we breathe plays its own subtle, yet significant, role in the ocean's enduring saltiness. As you settle into your comfortable spot, feeling the quiet rhythm of your own breath, imagine the vast blanket of air that surrounds our planet. This atmosphere, seemingly ethereal and intangible, is in constant, dynamic interaction with both the land and the oceans. It's a grand chemical exchange, a continuous conversation where elements move between the gaseous realm, the solid earth, and the liquid sea. Think of the air around you, filled with various gases. One of the most important for our story is carbon dioxide, CO2. This gas, naturally present in the atmosphere, is constantly being absorbed by rainwater as it falls through the sky. When carbon dioxide dissolves in water, it forms a weak acid called carbonic acid. This is the same weak acid that gives carbonated drinks their slight tang. Now, this slightly acidic rainwater isn't just a gentle cleanser, it's a tireless agent of change. As this carbonic acid-laced rainwater then falls upon the land, it greatly enhances the process of chemical weathering that we discussed in our first chapter. While pure water can dissolve minerals, this weakly acidic rainwater is even more effective at breaking down rocks and soils. It acts like a more potent solvent, accelerating the release of ions like calcium, magnesium, sodium, and potassium from silicate and carbonate rocks. So, in this way, the atmosphere, by providing carbon dioxide to rainwater, amplifies the amount of dissolved salts that rivers ultimately carry to the ocean. It's a subtle partnership, where the air works hand in hand with the water to extract more of the Earth's hidden mineral treasures. But the atmosphere's influence doesn't stop there. The surface of the ocean itself is constantly exchanging gases with the atmosphere. Gases like carbon dioxide directly dissolve into the ocean waters. Once dissolved, CO2 can react with water to form carbonic acid within the ocean itself, contributing to the ocean's acidity and participating in a complex series of chemical reactions that affect the availability of various ions. This process is crucial for marine life, especially creatures that build shells and skeletons from calcium carbonate. Consider other gases released into the atmosphere, particularly from volcanic activity, both on land and, as we learned, from those fiery vents beneath the sea. Volcanoes release various gases, including sulfur dioxide, SO2. When sulfur dioxide mixes with water vapor and oxygen in the atmosphere, it can form sulfuric acid. This strong acid, when it falls as acid rain, is another powerful agent of chemical weathering, contributing significantly to the dissolved sulfate and other ions that eventually make their way to the ocean. So, the Earth's internal fiery processes, which emit gases into the atmosphere, indirectly contribute to ocean salinity through atmospheric reactions and subsequent rainfall. Beyond these chemical interactions, there's also the subtle influence of atmospheric particles. Tiny dust particles, pollen, and even microscopic sea spray containing evaporated ocean salt can be carried high into the atmosphere by winds. While most of these eventually settle back to land or sea, they represent a continuous, albeit small, transfer of matter between the atmosphere and the Earth's surface, including the oceans. Imagine, as you drift deeper into your restful state, the constant, invisible dialogue between the sky above and the waters below. The atmosphere isn't just a passive observer, it's an active participant in the great chemical cycles of our planet. It acts as a conduit, a processing plant, and a partner in the continuous delivery of dissolved minerals to the ocean. The air we breathe, the clouds that gather, the rain that falls, all are part of this intricate system that helps define the very taste of our vast seas. This ongoing exchange highlights the interconnectedness of all Earth systems. The oceans, the land, and the atmosphere are not separate entities. They are deeply intertwined, each influencing the chemical composition and dynamics of the others. The saltiness of the ocean, therefore, is not simply a result of water flowing over rocks. It is a symphony of processes involving the very air that surrounds us, a testament to the Earth's holistic and self-regulating nature. Let this understanding settle over you. A gentle wave of insight. The atmosphere doesn't just provide us with breathable air or regulate our weather. It plays a subtle yet profound role in determining the very chemistry of our oceans. This quiet, continuous exchange, a testament to the tireless interaction of Earth's spheres, is a source of quiet wonder. It deepens our appreciation for the intricate, interconnected nature of the universe, where even the most ethereal elements contribute to the tangible characteristics of our world. Rest now with the gentle murmur of the atmosphere, subtly shaping the ocean's ancient saltiness, guiding you towards a truly peaceful slumber. Welcome back, peaceful traveler, as we continue our gentle exploration into why our vast ocean is salty. We've journeyed through the unseen paths of rainwater dissolving minerals from the land, delved into the fiery depths where undersea volcanic activity adds its unique chemical breath, and even looked skyward to understand the atmospheric contribution. Now, as you drift even deeper into your serene state, let us turn our attention to the simple, yet profound, process that ensures all these dissolved minerals, once delivered to the sea, remain there, patiently accumulating over eons the ceaseless cycle of water evaporation, leaving salts behind. As you settle into your comfortable spot, feeling the quiet stillness of your surroundings, imagine the colossal surface of our world's oceans, stretching for millions of square miles, constantly exposed to the warmth of the sun and the gentle kiss of the wind. This exposure sets in motion one of Earth's most fundamental processes, evaporation. The sun's energy gently warms the surface of the ocean, providing enough energy for water molecules to transform from a liquid state into an invisible gas, water vapor, which then rises silently into the atmosphere. Think of it like a gentle planetary distiller. When water evaporates from the ocean's surface, it is a remarkably selective process. Only the pure water molecules ascend into the sky. The salts and other dissolved minerals, those invisible passengers that rivers have carried from the land and hydrothermal vents have released from the deep, are too heavy and do not vaporize. They are left behind, patiently remaining in the ocean water. It's as if the ocean is a vast open-air pot, constantly boiling off pure water, leaving an ever-concentrating residue of salts. This pure water vapor, now floating in the atmosphere, eventually cools, condenses, and forms clouds. These clouds then travel, carried by the winds, over continents and land masses, where they release their fresh, pure water back to the Earth's surface as rain or snow. This fresh precipitation then begins its journey anew, trickling over rocks, dissolving more minerals, joining streams and rivers, and eventually flowing back to the ocean. And here lies the heart of the ocean's enduring saltiness. It's a one-way street for salts. Water continuously carries salts into the ocean, but the primary way water leaves the ocean, through evaporation, does not remove these salts. It's a perpetual cycle of input without significant output via this pathway. Over millions and billions of years, this constant replenishment of salts, coupled with their non-removal through evaporation, has led to their steady accumulation, transforming the vast freshwater primordial oceans into the briny seas we know today. Imagine, as you drift deeper into your restful state, this endless loop. The sun warms the water, and pure water rises invisibly to the sky, leaving behind the minerals it once carried. The pure water then falls as rain, begins its fresh journey over land, picks up new salts, and ultimately returns to the ocean, adding to the ever-present saline concentration. It's a testament to the patient, persistent work of natural processes, a slow accumulation over geological timescales that explains one of our planet's most defining characteristics. To truly grasp the power of evaporation in concentrating salts, consider examples of endorheic basins or salt lakes on land. These are lakes that have no outflow to the ocean. Rivers flow into them, but water only leaves by evaporation. A perfect example is the Great Salt Lake in Utah, or even the famously hypersaline Dead Sea between Israel and Jordan. Rivers, carrying dissolved salts, flow into these lakes. But because there's no outlet and evaporation rates are high in these arid regions, the water evaporates, leaving the salts behind. Over time, the concentration of salts in these lakes becomes incredibly high, far saltier than the ocean, to the point where they become crystallized salt flats. These landlocked lakes are like accelerated natural laboratories, demonstrating the fundamental principle of evaporation, leaving salts behind, leading to extreme salinity. The global ocean, while vast and interconnected, operates on this same principle, albeit on a much grander scale and with additional input and removal mechanisms that keep its salinity within a stable range, preventing it from becoming as hypersaline as the Dead Sea. The consistent input of riverine salts, combined with the continuous evaporation of pure water, forms the bedrock of the ocean's salinity. As you allow your consciousness to deepen, imagine the entire planet as a vast, interconnected system. The sun providing energy, the water transforming, the land patiently yielding its minerals, and the atmosphere acting as a silent transporter of pure water. It's a beautiful symphony of natural processes, all contributing to the unique character of our oceans. The fact that the ocean is salty is not an accident. It is the logical and inevitable outcome of these ceaseless cycles, patiently at work for billions of years. Let this understanding settle over you, a gentle wave of insight. The ocean's saltiness is a testament to the endless circulation of water on our planet, a continuous story of purity rising to the sky and dissolved secrets accumulating in the deep. This quiet, persistent process, a testament to the tireless interaction of Earth's spheres, is a source of quiet wonder. It deepens our appreciation for the intricate, interconnected nature of the universe, where even the simplest actions, repeated over unimaginable timescales, lead to profound and enduring characteristics. Rest now, with the gentle rhythm of evaporation and the enduring presence of salts, guiding you deeper into your peaceful slumber. Welcome back, peaceful traveler. As we continue our gentle exploration into why our vast ocean is salty, we've journeyed through the unseen paths of rainwater dissolving minerals from the land, delved into the fiery depths where undersea volcanic activity adds its unique chemical breath, and even looked skyward to understand the atmospheric contribution. We then revealed the profound secret of evaporation, which patiently leaves salts behind, concentrating them over eons. Now, as you drift even deeper into your serene state, let's discover that the ocean isn't merely a passive recipient of salts. It is a living, breathing chemical system with its own ingenious mechanisms for removing salts, ensuring a delicate and crucial balance. As you settle into your comfortable spot, feeling the quiet stillness of your surroundings, imagine the ocean not just as a static basin, endlessly accumulating. Instead, picture it as a vast, self-regulating chemical factory where processes are constantly at work, both adding and removing dissolved substances. This dynamic equilibrium is precisely why the ocean hasn't become increasingly saltier to the point of saturation over billions of years, like a landlocked salt lake. There are natural pathways that elegantly draw minerals out of the seawater, preventing it from becoming excessively briny. One of the most significant ways the ocean removes dissolved salts is through the formation of sediments and minerals on the seafloor. Many of the ions carried into the ocean by rivers or released by hydrothermal vents don't remain dissolved indefinitely. Over time, and under specific chemical conditions, these ions can react with each other or with other substances in the water to form new, solid, insoluble minerals. These newly formed minerals then precipitate out of the seawater, meaning they become solid and settle to the bottom of the ocean, becoming part of the vast layers of sediment on the seafloor. Think of it like a quiet, underwater snowfall of tiny crystals. For instance, calcium ions, which are abundant in seawater primarily from the weathering of limestone on land, can combine with bicarbonate ions to form calcium carbonate, KCO3. This is the very material that makes up chalk, limestone, and the shells of many marine organisms. When these calcium carbonate minerals form directly from seawater, or when the shells of marine life settle after death, they effectively remove calcium and carbonate from the dissolved state in the ocean. Similarly, other ions can combine to form clays, silicates, and various evaporate minerals like gypsum that also settle onto the ocean floor, locking away their chemical constituents. This process is continuous and incredibly vast, essentially locking away salts in the Earth's crust for geological timescales. Another remarkable mechanism for salt removal involves the activity of living organisms. The ocean is teeming with an incredible diversity of life, from microscopic plankton to colossal whales. Many of these organisms, especially those with shells, skeletons, or hard parts, actively extract specific ions from the seawater to build their structures. For example, countless marine organisms, including corals, clams, snails, and tiny foraminifera, pull calcium and carbonate ions from the water to construct their protective shells and sturdy skeletons. When these organisms die, their remains sink to the seafloor, forming vast deposits of calcium carbonate, such as limestone and chalk beds, thereby removing these ions from the water column. Imagine a coral reef, a vibrant underwater city built over centuries. Each tiny coral polyp is a living testament to the ocean's ability to recycle and remove dissolved minerals. As these creatures extract calcium and carbonate, they contribute to the ocean's chemical balance, acting as biological filters that help keep the salinity in check. This biological uptake is a powerful, ongoing process that demonstrates the intimate connection between life and the chemical composition of our planet. Furthermore, those deep-sea hydrothermal vents we discussed earlier also play a role in removing some salts, not just adding them. While they certainly inject new minerals, the superheated seawater reacting with hot rock beneath the vents also leads to the removal of certain elements, notably magnesium and sulfate, from the circulating seawater. As the water passes through the hot crust, these ions react with the rocks and are incorporated into new minerals that become part of the oceanic crust itself, effectively being filtered out of the water. This means that these powerful underwater systems are not just one-way suppliers of minerals. They are complex chemical reactors that both add and subtract from the ocean's dissolved content, contributing to its overall chemical regulation. Imagine, as you drift deeper into your restful state, the silent, ceaseless work happening across the ocean's depths. Picture countless tiny crystals slowly forming and settling, microscopic organisms diligently building their homes from dissolved minerals, and superheated water circulating through the Earth's crust, subtly removing elements. These are the ocean's elegant self-regulating mechanisms, working tirelessly to maintain a delicate chemical balance. This intricate dance of input and output, of adding and removing, ensures that the ocean's salinity remains remarkably stable over geological time. It's a testament to the Earth's interconnected systems, demonstrating that the ocean is not a static pool, but a dynamic, living entity that actively manages its own chemistry. The understanding that the ocean has these natural drainage systems for salts provides a profound sense of the wisdom and self-organizing capacity of nature. Let this understanding settle over you, a gentle wave of insight. The ocean's saltiness is not just a result of continuous input, it is a meticulously managed balance, constantly adjusted by these natural removal processes. This quiet, persistent self-regulation, a testament to the tireless interaction of Earth's spheres and its living inhabitants, is a source of quiet wonder. It deepens our appreciation for the intricate, interconnected nature of the universe, where even the vast, seemingly endless oceans maintain a precise chemical equilibrium. Rest now, with the gentle rhythm of the ocean's self-balancing chemistry, guiding you deeper into your peaceful slumber. Welcome back, peaceful traveler. As we continue our gentle exploration into why our vast ocean is salty, we've journeyed through the unseen paths of rainwater dissolving minerals from the land, delved into the fiery depths where undersea volcanic activity adds its unique chemical breath, and looked skyward to understand the atmospheric contribution. We then revealed the profound secret of evaporation, which patiently leaves salts behind, concentrating them over eons. And in our last quiet chapter, we discovered the ocean's ingenious mechanisms for removing salts through mineral formation and the tireless work of living organisms. Now, as you drift even deeper into your serene state, let us bring all these threads together to understand the remarkable concept of dynamic equilibrium, explaining why the ocean's saltiness has remained so incredibly stable for millions of years. As you settle into your comfortable spot, feeling the quiet stillness of your surroundings, imagine the ocean not as a static body of water, but as a living, breathing chemical system in a state of perpetual, delicate balance. For all the reasons we've discussed, rivers constantly pouring in dissolved minerals from the land, hydrothermal vents injecting new elements from the Earth's crust, and evaporation leaving salts behind, you might expect the ocean to simply get saltier and saltier over time, becoming an impossibly briny solution. Yet, scientific evidence tells us that the ocean's average salinity has been remarkably constant for hundreds of millions of years, if not longer. This stability is the beautiful hallmark of a dynamic equilibrium. Think of it like a bathtub, with the faucet running and the drain open. Water is continuously flowing into the tub from the faucet, and water is continuously flowing out of the tub through the drain. If the rate at which water flows in is exactly matched by the rate at which water flows out, the water level in the tub will remain constant, even though water is constantly moving both in and out. The ocean operates on a similar principle, but instead of just water, it's a constant flow of dissolved salts. In the grand cosmic bathtub that is our ocean, the inputs are vast and continuous. Chemical weathering of continental rocks. Rain and rivers tirelessly dissolve minerals from the land, delivering ions like sodium, chloride, calcium, and bicarbonate to the sea. Volcanic activity and hydrothermal vents. Undersea vents gush hot, chemically altered water, releasing elements like sulfur, sea iron, and manganese into the deep ocean. Atmospheric deposition. Gases like carbon dioxide dissolve into rainwater and directly into the ocean, contributing to chemical weathering and ocean chemistry. Simultaneously, the outputs are equally vital and continuous, patiently removing salts from the ocean. Formation of sediments and minerals. Ions in seawater combine to form insoluble minerals like calcium carbonate, silicates, and clays that precipitate out and settle to the seafloor, effectively locking away these elements. Biological activity. Marine organisms, from corals to shell-building plankton, actively extract specific ions like calcium and carbonate to build their shells and skeletons. When they die, these materials become part of the ocean floor, removing the ions from the water column. Reactions at hydrothermal vents. While adding some elements, the superheated water at hydrothermal vents also removes other elements, such as magnesium and sulfate, as it reacts with the hot crustal rock. The remarkable truth is that, over geological timescales, the rate at which salts and other dissolved minerals are added to the ocean is roughly balanced by the rate at which they are removed. This isn't a static balance like a perfectly still seesaw. Instead, it's a dynamic balance, where immense quantities of material are constantly entering and leaving the ocean, but the overall concentration of salts remains remarkably stable. It's a continuous, self-regulating process that has been finely tuned over billions of years of Earth's history. Consider the profound implications of this stability. The very life that thrives in our oceans, from the simplest single-celled organisms to the largest whales, has evolved and adapted to a relatively consistent level of salinity. If the ocean were to become progressively saltier without a removal mechanism, or if its saltiness fluctuated wildly, marine ecosystems would struggle to survive. This long-term stability of ocean salinity is therefore not just a fascinating chemical curiosity. It is a fundamental environmental condition that underpins the vast biodiversity and productivity of our planet's aquatic realms. Imagine the ocean as a magnificent, ancient clockwork mechanism, constantly whirring, adding and removing chemical components with precise timing. Each input and output mechanism is like a gear, turning in perfect synchronicity to maintain the overall balance. It's a testament to the Earth's inherent ability to regulate its own systems. A living, breathing planet, maintaining its vital chemistry through complex, interconnected cycles. This understanding brings a profound sense of awe, realizing that the very taste of our oceans is a reflection of this grand, planetary balancing act. This concept of dynamic equilibrium is central to understanding many of Earth's long-term cycles. Not just ocean salinity, it shows us that our planet is a complex, self-organizing system where seemingly disparate processes are intricately linked. The geological forces that uplift mountains and create volcanoes, the atmospheric forces that drive weather and chemical reactions, and the biological forces that govern life, all play a part in maintaining the delicate chemical balance of our oceans. As you allow your consciousness to deepen, imagine the vast, shimmering surface of the ocean, beneath which lies a quiet, tireless chemical laboratory. Elements are constantly flowing in and constantly flowing out, yet the overall composition remains steadfast. This reassuring stability is a direct consequence of dynamic equilibrium, a cosmic dance of inputs and outputs that ensures the ocean's enduring character. Let this understanding settle over you. A gentle wave of insight. The ocean's consistent saltiness is not a static state, but a vibrant, active balance of countless processes working in concert. This quiet, persistent self-regulation, a testament to the tireless interaction of Earth's spheres and its living inhabitants, is a source of quiet wonder. It deepens our appreciation for the intricate, interconnected nature of the universe, where even the vast, seemingly endless oceans maintain a precise chemical equilibrium. Rest now, with the gentle rhythm of the ocean's self-balancing chemistry, guiding you deeper into your peaceful slumber. Welcome back, peaceful traveler, as we continue our gentle exploration into why our vast ocean is salty. We've journeyed through the unseen paths of freshwater dissolving minerals from the land, delved into the fiery depths where undersea volcanic activity adds its unique chemical breath, and looked skyward to understand the atmospheric contribution. We then revealed the profound secret of evaporation, which patiently leaves salts behind, concentrating them over eons. We also discovered the ocean's ingenious mechanisms for removing salts, ensuring a delicate and crucial balance, leading to a state of dynamic equilibrium. Now, as you drift even deeper into your serene state, let us embrace a more nuanced understanding. The salt in the ocean is far more than just table salt. It's a rich, complex cocktail of diverse dissolved minerals, each with its own story and origin. As you settle into your comfortable spot, feeling the quiet stillness of your surroundings, imagine dissolving a pinch of the salt you might use in your kitchen into a glass of water. That familiar white crystalline substance is primarily sodium chloride, NaCl. This is indeed the most abundant salt in the ocean, giving it much of its characteristic taste. However, the ocean is a far more chemically intricate solution than just salty water. It's a vast dynamic chemical brew containing a fascinating array of elements, all dissolved in various ionic forms. Think of the ocean as a giant, liquid mineral museum, holding countless dissolved treasures. While sodium chloride makes up the vast majority, approximately 85% of the dissolved solids in seawater, there's a significant remaining 15% that consists of other vital chemical players. Like these include magnesium ions, Mga2+. These are the second most abundant positive ions in seawater. They contribute to the ocean's bitterness and are crucial for many biological processes, like photosynthesis in marine algae. They primarily originate from the weathering of rocks on land and are also significantly cycled through hydrothermal vents, where some are removed. Sulfate ions. Olo4. 2. These are abundant negative ions, contributing to the overall salinity. They are primarily introduced through the weathering of sulfate-rich rocks on land, and also from volcanic gases dissolving in rainwater and directly into the ocean. Calcium ions, Ca2+. These are vital building blocks for marine life. As we discussed, countless organisms, from corals to shell-forming plankton, extract calcium to build their hard parts. Calcium largely comes from the weathering of limestone and other calcium-rich rocks on land. Potassium ions K+. Another important positive ion. Potassium is essential for various biological processes and is released through the weathering of terrestrial rocks. Bicarbonate ions, HCO3. These play a crucial role in the ocean's buffering capacity, helping to regulate its pH, and are formed when atmospheric carbon dioxide dissolves in water. They are key in the formation of carbonate minerals. And then, there are trace elements, tiny amounts of almost every element found on Earth, from minute quantities of gold and silver to iron, zinc, copper, and iodine. While present in very small concentrations, many of these trace elements are biologically important, acting as essential nutrients for various marine organisms. Each of these ions, whether abundant or in trace amounts, has its own unique journey into the ocean. Some, like sodium and chloride, are predominantly carried by rivers from the long, slow process of continental weathering. Others, like sulfur and certain metals, find a significant pathway into the ocean through the fiery breath of undersea hydrothermal vents and volcanic emissions. Still others, like bicarbonate, are strongly linked to the exchange of gases with the atmosphere. It's a complex tapestry of inputs, with different sources contributing different chemical threads to the ocean's overall composition. Imagine, as you drift deeper into your restful state, a vast invisible chemical fingerprint that defines our ocean. This fingerprint is made up of the precise proportions of all these different dissolved ions. This chemical signature is incredibly stable over vast areas of the open ocean, a testament to the efficient mixing of ocean currents and the long timescales over which these processes operate. While the overall salinity, the total amount of dissolved salts, can vary slightly in different regions, the relative proportions of these major ions remain remarkably constant in the open ocean around the world. This consistency allows marine life to thrive, as organisms have evolved to depend on these stable chemical conditions. This understanding of the diverse chemical composition of ocean water paints a much richer picture than simply salty. It reveals the ocean as a dynamic, living solution, constantly processing and balancing a myriad of chemical elements. It's a testament to the Earth's intricate geological, atmospheric, and biological cycles, all working in concert to create and maintain this unique and vital environment. The very taste of the ocean, therefore, is not a simple sensation, but a complex symphony of flavors, each note a dissolved mineral telling a story of its journey from land, from deep within the earth, or from the sky above. Let this understanding settle over you, a gentle wave of insight. The ocean's chemical makeup is a profound reflection of Earth's continuous interconnected processes, a silent testament to the countless reactions occurring across its vast expanse. This quiet, persistent chemical dance, a testament to the tireless interaction of Earth's spheres, is a source of quiet wonder. It deepens our appreciation for the intricate, interconnected nature of the universe, where even the most seemingly simple characteristics hold a hidden world of complexity and balance. Rest now, with the gentle rhythm of the ocean's complex chemistry, guiding you deeper into your peaceful slumber. Welcome back, peaceful traveler. As we continue our gentle exploration into why our vast ocean is salty, we've journeyed through the unseen paths of freshwater dissolving minerals from the land, delved into the fiery depths where undersea volcanic activity adds its unique chemical breath, and looked skyward to understand the atmospheric contribution. We then revealed the profound secret of evaporation, which patiently leaves salts behind, concentrating them over eons. We also discovered the ocean's ingenious mechanisms for removing salts, ensuring a delicate and crucial balance, leading to a state of dynamic equilibrium. And we embraced the nuanced understanding that the salt in the ocean is a rich, complex cocktail of diverse dissolved minerals, far beyond just table salt. Now, as you drift even deeper into your serene state, let us explore a surprising truth. The ocean's saltiness is not uniformly distributed. Instead, it varies across the globe, painting a diverse and dynamic picture of the world's waters. As you settle into your comfortable spot, feeling the quiet stillness of your surroundings, imagine the vast, interconnected expanse of the global ocean. While we've spoken of the ocean's average salinity and the remarkably constant proportions of its major dissolved ions, the total amount of dissolved salt in seawater can actually differ significantly from one region to another. These variations are driven by a fascinating interplay of atmospheric conditions, freshwater inputs, and the powerful forces of ocean currents. Think of it like a quilt made of many different fabrics, each with its own subtle texture. While it's all part of the same grand blanket, each patch tells a slightly different story. The salinity of ocean water is typically expressed in parts per thousand ppt, or practical salinity units PSU, with the average global ocean salinity being around 35 ppt, or 35 PSU. This means that for every 1,000 grams of seawater, there are about 35 grams of dissolved salts. But this is just an average, and specific regions can be notably saltier or fresher. So, what are the primary factors that cause these variations in ocean salinity? One of the most significant factors is evaporation. Remember how evaporation leaves salts behind? In regions where the air is warm and dry and winds are high, the rate of evaporation from the ocean surface is significantly increased. Think of the subtropical regions, particularly in the middle of the Atlantic and Pacific Oceans, where the sun is intense and rainfall is relatively low. Here, the continuous removal of pure water through evaporation, leaving the salts behind, leads to higher surface salinities. The North Atlantic, for instance, is notably saltier than the global average. Partly due to strong evaporation, it's like a natural process of concentration, where the sun's energy relentlessly distills pure water from the ocean, leaving behind a more concentrated, briny solution. Conversely, areas that receive substantial freshwater input tend to have lower salinities. This freshwater can come from two main sources: precipitation, rainfall, and snowfall regions with very high rainfall, such as near the equator and the tropical rainforest belts, receive a continuous deluge of fresh water from the sky. This fresh rainwater dilutes the surface seawater, reducing its salinity. Imagine countless raindrops falling into the ocean, each one a tiny act of sweetening the vast briny expanse. River runoff coastal areas, especially near the mouths of large rivers, experience significant dilution from the constant influx of fresh water from land. The Amazon River, for example, pours such an enormous volume of fresh water into the Atlantic Ocean that its influence on salinity can be detected hundreds of miles out to sea. Estuaries, where rivers meet the sea, are classic examples of areas with highly variable and often much lower salinities. Another fascinating factor influencing salinity is the formation and melting of sea ice. When seawater freezes to form sea ice, a remarkable process occurs. The vast majority of the salts are expelled from the ice structure. Think of it like the ocean actively pushing out its salt to create fresh ice. This means that the remaining unfrozen seawater in the immediate vicinity becomes denser and significantly saltier. This process is particularly pronounced in the polar regions, around the Arctic and Antarctic. Conversely, when this sea ice melts, it releases relatively fresh water back into the ocean, diluting the surface waters and lowering salinity in those areas. This freeze-thaw cycle of sea ice is a powerful mechanism for influencing local ocean salinity. Imagine, as you drift deeper into your restful state, a global map of ocean salinity, not as a uniform blue, but as a vibrant mosaic of blues and greens, yellows and reds, each color representing a different level of saltiness. The warm, dry belts would show deeper blues, indicating higher salinity. The equatorial regions with their abundant rains, and the polar regions with their melting ice, would shimmer with lighter hues, denoting lower salinity. It's a dynamic, ever-changing portrait, influenced by the sun, the winds, the land, and the very ice that forms on its surface. These variations in salinity are not just idle curiosities, they play a crucial role in driving the vast, global ocean currents, particularly the deep ocean circulation. Saltier, denser water tends to sink, while fresher, lighter water tends to remain at the surface. This density difference, combined with temperature variations, creates a powerful thermohaline circulation, thermobanyadran heat, haline, almonine salt, that acts like a vast, slow-moving conveyor belt, transporting heat, nutrients, and dissolved gases around the entire planet. So, the subtle variations in ocean saltiness are fundamental drivers of Earth's climate system, connecting distant parts of the globe in a grand, unseen liquid dance. Let this understanding settle over you, a gentle wave of insight. The ocean's saltiness is not a monotonous constant, but a dynamic and varied characteristic, constantly influenced by the ebb and flow of planetary processes. This quiet, persistent variation, a testament to the tireless interaction of Earth's spheres, is a source of quiet wonder. It deepens our appreciation for the intricate, interconnected nature of the universe, where even the seemingly uniform vastness of the ocean holds a hidden world of diverse chemical landscapes. Rest now, with the gentle murmur of the ocean's varied saltiness, guiding you deeper into your peaceful slumber. Welcome back, peaceful traveler. As we continue our gentle exploration into why our vast ocean is salty, we've journeyed through the unseen paths of freshwater dissolving minerals from the land, delved into the fiery depths where undersea volcanic activity adds its unique chemical breath, and looked skyward to understand the atmospheric contribution. We then revealed the profound secret of evaporation, which patiently leaves salts behind, concentrating them over eons. We discovered the ocean's ingenious mechanisms for removing salts, ensuring a delicate and crucial balance, leading to a state of dynamic equilibrium. We embrace the nuanced understanding that the salt in the ocean is a rich, complex cocktail of diverse dissolved minerals, and we even explored how salinity varies across the globe, painting a dynamic picture of the world's waters. Now, as you drift even deeper into your serene state, let us journey back in time to the very earliest chapters of Earth's history and contemplate the ancient oceans and their primordial saltiness, the very cradle from which life emerged. As you settle into your comfortable spot, feeling the quiet stillness of your surroundings, imagine our planet as it was billions of years ago, a nascent world still cooling from its fiery birth. The first oceans, vast bodies of water, began to condense from atmospheric water vapor as the Earth cooled enough for liquid water to exist on its surface. These earliest oceans would have been far from the familiar salty seas we know today. They would have been closer to freshwater, perhaps even slightly acidic, as carbon dioxide from the early atmosphere dissolved into them. However, the processes that contribute to ocean salinity today, the chemical weathering of rocks and volcanic activity, were even more vigorous in the Earth's early, turbulent history. The young Earth was a geological powerhouse. Volcanic eruptions were far more frequent and intense than they are now. spewing vast quantities of gases and minerals into the atmosphere and directly into the nascent oceans. Imagine countless undersea volcanoes actively pumping out hot, mineral-rich fluids, contributing rapidly to the ocean's chemical composition. The weathering of the newly formed continental crust would also have been more aggressive, as fresh rock surfaces were continuously exposed to the elements and acidic rainwater. So, while starting as fresh water, these early oceans would have quickly begun accumulating dissolved minerals at a much faster rate than today. The question of whether the early oceans were saltier or less salty than today's oceans is a fascinating area of scientific inquiry, and it's complex. Some theories suggest that the initial influx of salts from intense volcanic activity and rapid weathering might have made them quite saline, perhaps even hypersaline in localized areas, before the removal mechanisms fully established their balance. Other models propose that certain ions might have been more abundant or less abundant at different periods, depending on the prevailing geological and atmospheric conditions. What is certain is that the ocean's chemical composition has been continuously evolving alongside the Earth's geological and biological history. Crucially, it was within these ancient, developing oceans, with their unique and evolving chemical composition, that life itself first emerged. The primordial soup, that mythical cradle of life, was literally a salty solution. The dissolved ions, sodium, potassium, calcium, magnesium, chloride, sulfate, and a myriad of trace elements, were not just passive components of the water, they were the very building blocks, the chemical ingredients, that enabled complex biochemical reactions to begin. The availability of these specific ions, in specific concentrations, was fundamental for the formation of the first cells, the development of early metabolic pathways, and the eventual flourishing of marine ecosystems. Imagine the earliest forms of life, microscopic and fragile, delicately balanced within this ancient, briny environment. Their very existence was intertwined with the ocean's chemistry. Over billions of years, as the ocean's salinity stabilized into the dynamic equilibrium we see today, life adapted and evolved, becoming intricately attuned to these specific chemical conditions. Our own bodies, for instance, carry within them a legacy of the ocean's ancient saltiness. The salinity of our blood and the chemical composition of our cells remarkably resemble that of ancient seawater, a testament to our evolutionary origins in the ocean. It's a deep, personal connection to the vast, salty sea. So, the saltiness of the ocean is not merely a physical characteristic, it is a profound historical record, a chemical signature of Earth's tumultuous past and the incredible journey of life. It speaks of a time when volcanoes roared and continents shifted, when rain fell for millennia, and when, amidst this dynamic chemical brew, the first sparks of life ignited. The ocean, with its enduring saltiness, truly is the great womb of life, providing the necessary conditions for everything that came after. As you allow your consciousness to deepen, let this grand, ancient story of the ocean's saltiness and its profound connection to the origins of life settle into your mind. Imagine the primordial seas, vast and powerful, teeming with the chemical ingredients for creation. This understanding offers a deep sense of continuity, connecting you to the very beginnings of our planet and the incredible resilience of life. Let this knowledge wash over you, a gentle wave of awe and serenity. The ocean's saltiness isn't just about chemistry, it's about life, history, and the continuous unfolding of our planet's epic story. This quiet, persistent chemical evolution, a testament to the tireless interaction of Earth's spheres and its living inhabitants, is a source of quiet wonder. It deepens our appreciation for the intricate, interconnected nature of the universe, where even the most fundamental properties hold a hidden history. Rest now, with the gentle murmur of the ancient ocean, carrying the whispers of early life, guiding you deeper into your peaceful slumber. Welcome back, beloved dreamer. for one final gentle whisper from the sleepy scientist. We have journeyed together through the tranquil depths of scientific inquiry, softly unraveling the profound mystery of why our ocean is salty. We began by tracing the unseen paths of rainwater dissolving minerals from the land, a patient process amplified by the atmosphere's breath. We then delved into the fiery depths, discovering how undersea volcanic activity and hydrothermal vents add their unique chemical signatures to the vast waters. Our exploration continued as we revealed the profound secret of evaporation, which tirelessly leaves salts behind, concentrating them over eons. But we also discovered the ocean's ingenious mechanisms for removing salts through mineral formation and the tireless work of living organisms, ensuring a delicate and crucial dynamic equilibrium. We embrace the nuanced understanding that the salt in the ocean is a rich, complex cocktail of diverse dissolved minerals, far beyond just table salt, and explored how salinity varies across the globe, painting a dynamic picture of the world's waters. Finally, we journeyed back in time to the ancient oceans and their primordial saltiness, the very cradle from which life itself emerged, connecting us to the deep history of our planet. As you lie here, fully relaxed, perhaps feeling the gentle pull of sleep drawing you deeper, let all these insights coalesce into a single, profound understanding. The saltiness of our ocean is not a simple accident or a singular event. It is a magnificent, ongoing saga, a testament to the continuous, interconnected processes that define our living planet. It is a story woven from the patient erosion of continents, the fiery breath of the Earth's interior, the subtle chemistry of the atmosphere, and the tireless work of countless living organisms. Each drop of ocean water holds within it billions of years of geological and biological history, a liquid memory of Earth's grand evolution. Think of the reassuring constancy this understanding brings. Despite the continuous input of salts from rivers and vents, the ocean has maintained a remarkably stable salinity for millions upon millions of years. This incredible balance, this dynamic equilibrium, is a testament to nature's profound ability to self-regulate. It's a vast global chemical dance where inputs are precisely matched by outputs, ensuring that the conditions necessary for marine life, and by extension, all life on Earth, remain stable and predictable. This deep, consistent characteristic of our ocean is not merely a scientific curiosity. It is a fundamental pillar supporting the vast biodiversity and ecological richness of our blue planet. This journey through oceanography isn't just about learning facts. It's about connecting with something infinitely vast and intimately vital to our existence. When you next smell the scent of the sea or hear the rhythmic crash of waves, you now carry a deeper appreciation for the profound chemical story unfolding within every drop. You know that you are intrinsically linked to the ocean's ancient chemistry, that the very composition of your own body reflects the saline waters from which all life emerged. It's a universal connection, a reminder that we are all interwoven into the vast, beautiful fabric of Earth's natural cycles. There is a deep serenity in this knowledge. To understand the elegant processes that govern the ocean's saltiness is to find a sense of calm in its boundless expanse. It's to realize that even in the face of its immense size, there is profound order and intricate balance. The ocean doesn't operate on whims or chance. It follows timeless, predictable principles. And within that predictability, there is a gentle, comforting rhythm, a chemical heartbeat that has pulsed for eons and will continue to do so for eons to come. Our salty ocean is a living, breathing testament to the Earth's dynamic nature, constantly shaping and sustaining the world around us. So, as your mind quiets and your body grows heavy with peaceful sleep, take a moment to reflect on this profound connection to our briny seas. Imagine yourself drifting in the gentle currents of the ocean, feeling the quiet certainty of its ancient chemistry. Secure in the knowledge that this vast body of water, ever-present and ever-changing, maintains a perfect balance. Our Earth is a magnificent, self-regulating system, and the ocean's enduring saltiness is a shining example of its profound wisdom, patiently sustaining life through its ceaseless chemical dance. This knowledge isn't meant to keep you awake with wonder, but to lull you into a deeper, more profound state of rest, knowing that the very essence of our planet's greatest feature is a story of magnificent, ongoing harmony. Let the quiet certainty of these cosmic truths become a soothing lullaby. Feel the profound connection between your own stillness and the silent, majestic cycles of our planet. The very water that sustains you, the air you breathe, the ground beneath you, all are part of this incredible ongoing natural symphony. There's no need to grasp or to strive. Simply let go and allow the universe's inherent order to carry you into a peaceful, dream-filled slumber, guided by the gentle, everlasting story of why our ocean is salty